Hi students, welcome again. Today I am going to talk about another experiment which is named as the determination of conductance of a solution. Today I will show you how to determine the conductance of the solution, and after that how to determine the ionization ionization degree of that solution, and lastly to determine the equilibrium constant of that solution. Okay, so let's first start what is specific conductance. Specific conductance, if we talk about water, this is simply how water can conduct electricity, right? Electric current. And as you know, conductivity increases with increasing amount of the solution, or the amount of solute, sorry. And of course, if you have a lot of ions, then the mobility increases the conductivity. So you might have guessed what would be the conductivity of the distilled water and what would be the conductivity of the fresh water. As we say, distilled water, it's like, there's a rid of the ions, so of course the conductivity is very, very low. The conductivity of the distilled water ranges from 0.5 to 3 microsiemens per centimeter, whereas the conductivity of the fresh water is usually from 150 to 500 microsiemens per centimeter. After this, now let's go towards the conductance. As you have learned from your lecture classes, that conductance is equal to the inverse of resistance, and the conductance usually increases with the cross-sectional area, and it is inversely related to the length of the wire. So you can imagine, the high tension wire that we can see in the around the road, in the some regions, right? So they have big wires. They have they have high cross-sectional area. This is to increase the conductance, and you can also imagine that whenever we have long wires, then of course the conductance of the electricity decreases actually, right? So now let's go towards the main focusing of our experiment. So conductivity of a solution increases with the concentration. And what about the specific conductance, which is represented by L? This is actually decreases with increase in concentration. So you can see conductivity increases with the concentration, with increment of concentration, whereas equivalent conductance, it decreases with the increase in concentration. And the equivalent conductance of KCl, potassium chloride, which is one of the solutions that we are using today, it has the value of 0.014986 meter square per equivalent per ohm at 25 degrees centigrade. Today we are using two solutions. One solution is the strong electrolyte KCl, and another one is weak electrolyte, which is acetic acid CS3COS, right? So as you know, for weak electrolyte, you can see it has less degree of ionization. So you can see here the equilibrium is shifting back towards here, and then let's suppose you have the time 0 at initial condition. Let's suppose the concentration of this acetic acid is C, right? And at that time the ions will be 0, right? But after some time, let's suppose T is equal to 1, and at that time you'll have the concentration of these ions to be C alpha. That means the concentration of the CS3COS would be C minus C alpha, right? The remaining concentration. So of course you know from your lecture class, the equilibrium constant C alpha is equal to from here this times this C square alpha squared by this minus C alpha, as you can see here. So of course you will get it C alpha squared by 1 minus alpha. So this is your value, right? So now let's get some idea of determination of ionization degree. Ionization degree for weak electrolyte would be equal to the L by L naught. So I have already talked about L, which is the equivalent conductance, right? And this L naught, this is the limiting equivalent conductance. You can find this from the graph. when you plot L and square root of concentration. I'll talk more about this later, right? So to determine the Kc, which is our ultimate aim, now you can put the value of the alpha from this equation here. So the value, so now your Kc would be 3 times L by L naught square. This is the value of alpha by 1 minus L by L naught. So from here, now you'll get the value of Kc. But I mean, what we will use actually Ostwald's dilution law to determine the value of Kc. So as you know, Ostwald's dilution law, this is the equation here, right? So what we do is we will plot this 1 by L with the and against this Cl, right? So you can say y equal to mx plus c, right? This is your equation, right? When you plot it, right? So when you plot Cl and 1 by L from here, 1 by Cl and 1 by L, right? So your slope would be this value, 1 by Kc L naught e square, right? So from here you can find the value of Kc easily, right? So from this you'll find value of L naught, and from this the data, right? When you plot Cl by Cl and against 1 by L, right? You'll find the value of Kc. So this is the simple theory behind the experiment. So let me show you how to do this experiment, right? So you can see here. So I have like prepared three different solutions of the KCl and CS3COS acetic acid, right? So first you can prepare the struck solution of 0.02 molar of KCl, which is struck light, and same like 0.02 molar of the without light, okay, CS3COS, right? And you can dilute them, right? I mean, you can dilute like first you can dilute 1 by 4 and 1 by 8 or 1 by 16, right? And then same you can do the same dilution 1 by 4, 1 by 8, 1 by 16, all right? And then now we have connected, okay? So we have connected this Laguerre-Pro, Lab Pro you have already used in your general chemistry laboratories. So I don't have to teach you to use this Laguerre-Pro and Lab Pro. So what you do is you will, this is your conductance sensor, right? So you'll put this one here, you'll immerse this one here, still slowly, and then record the value that you have here. This is your specific conductance, right? So you will repeat, every time, as you know, you have to watch this conductometric sensor here, right? Every time when you use for one solution, okay? So every time you have to repeat it and find the value of the specific conductance, right? Once you have a specific conductance and you have the concentrations of the solutions, and you are done, okay? You are done. So you have to simply, put your values here, and you can get the required alpha, which is your ionization degree, and the value of Kc. That's the ultimate aim of our experiment. I'll send you the raw data today, and then you would use the raw data and you can write a report for me. Thank you.